In this difficult example, we're going to show that the formula for the volume of a pyramid can be found using integration. First, let us correct two small mistakes in the task. Let us remove this one sentence here. It makes no sense, and correspondingly here the equals x should not be. So we want to find the volume of a pyramid with square base by approximating it with cuboids. To that goal, we cut the pyramid into 4 equally high slices, and then we name the side lengths of the square cross sections AK. So here we have A1, A2, A3, and A4. The cutting was done so that all the 4 slices have the same height. For our calculations, we will need to look at the vertical cross section of the pyramid, which is also shown here on the right. The horizontal lines here correspond to A1, A2, A3, and A4 up here. Let us use delta x for the distance between the lines, which corresponds exactly to the height of each of the slices, and is obviously h total height divided by 4. Let now xk be the height at which the slice k was cut. So for example, slice 1 up here is cut at this height, the height being measured from the top. Slice k is measured at this height, and so on. And we see that x1 is just delta x here, x2 here is just 2 times the delta x, and so on again. For similarity reasons, we see that A1, the ratio A1 to delta x, or sorry, to x1, so A1 to x1 is equal to the ratio A2 to x2, A3 to x3, and so on. So all of it is equal to the ratio S to H. So we can reformulate that as AK divided by XK is equal to S divided by H. And solving this for AK, we get AK is S divided by H times XK. I call this 1 to be able to reuse it later. And using that XK is K times delta X, we get here S divided by H times K times delta X, which I mark as equation 2. Now let us find an upper estimate for the volume of the pyramid's upper estimate U4 by using 4 cuboids as shown in picture 3 here. The 4 cuboids, C1, C2, C3, and C4, they all have a square base, and the side lengths of these squares exactly correspond to A1, A2, A3, and A4. The height of the cuboids is delta x, obviously, a quarter of the total height. Note that each of the cuboids is larger than the corresponding slice of the pyramid, and hence using these 4 cuboids we are overestimating the real volume. We're getting an upper estimate. Now let us find the volume of cuboid k, which is actually just ak squared times delta x. And using 1, this becomes S divided by H times xk, the whole thing squared, times delta x. And let me name that 3. The upper estimate U4 is the sum of the volumes of the 4 cuboids, so V1 plus V2 plus V3 plus V4, which means we can write it in sigma notation as sum of k equals 1 to 4 of Vk. And inserting 3, we get sum of k going from 1 to 4 of S divided by H times xk squared times delta x. And let us name this 4. Now let us look at the corresponding lower estimate of the volume of the pyramid, which is shown in the last picture here, in the 4th picture. And we see there are only 3 cuboids left, because what happens, we're putting the cuboid inside the pyramid. So the first cuboid has actually volume 0, it's just a line, and all the other cuboids only have moved by 1 down. And the last cuboid, cuboid 4, is nowhere anymore, so this means L4 is just V1 plus V2 plus V3. And we get for the difference delta 4 between upper and lower estimate that equals exactly to volume 4, which using number 3 is just S divided by H times X4, the whole thing squared, times delta X. And using that X4 is actually S, we get S to the power of 4 divided by H squared times the delta X, which is H divided by 4. And let me name that number 5. We could obviously simplify this by cancelling out H versus H squared, but we'll leave that for the moment. Now let us find the formula for the upper estimate of the volume when we're using n cuboids, which means Un is V1 plus V2 plus and so on plus Vn. So the sum for k going from 1 to n of Vk, so the sum k going from 1 to n of S divided by H times xk squared times delta x. I have just used the number 4 and replaced actually the 4 by the n. All the rest remains the same. The difference delta n between the upper and lower estimate again corresponds to the volume of the bottom cuboid, which in this case is just Vn, and we can use the formula 5, which means it is S to the power of 4 divided by H squared times H divided by n. Nothing else has changed, just the 4 has become n. The latter is the case because H divided by 4 or H divided by n just represents the height of the cuboid, while the base face of the cuboid is always the base face of the pyramid, so that's why it doesn't change that part. And here now let's simplify it, so we get S to the power of 4 divided by H times 1 divided by n. Now we come to the last step. Let us see what happens when n goes to infinity. So insert for Un just the upper result. And since the ak are just k times delta x, we should realize that this is exactly the definition of the integral. So I have the integral of s divided by h, here h times x, squared dx. And from where to where is the x moving or going? It starts at 0 here and goes down until h. So we have to insert as borders 0 to h. So let us expand the brackets, and we get s squared divided by h squared, which is a constant with respect to this integration, so I can take it in front of the integral. So I get this times the integral of x squared dx, still from 0 to h, which is then s squared divided by h squared times x to the power of 3 divided by 3, integrated from 0 to h. What remains is s squared divided by h squared times h to the power of 3 divided by 3. I skip the minus 0, cancelling out the to the power of 3 against the h squared here. I get in the end 1/3 times s squared times h, and replacing the s squared by base phase g, I get 1/3 times g times h, the well-known formula. Let us also look at what happens with the difference delta n between upper and lower estimate when n goes to infinity. So we get it's the limit for n going to infinity of Vn, which means the limit of n going to infinity of s to the power of 4 divided by h times 1 divided by n. And as we see, s to the power of 4 divided by h is just again a constant, but this 1 divided by n goes off to 0, so the whole thing is 0. So we have found out that the limit of the lower estimate is the same like the limit of the upper estimate, which means this is really the volume of the pyramid, and we have shown the volume of the pyramid is hence this 1/3 GH as we wanted to show.